Let's talk about why ionic bonds form and exactly how they form. So first of all, they want to form because they want to be stable. And we're really talking about what the outermost shell electrons are doing. All atoms want to have the great 8, unless it's a smaller atom, and then they're happy with just having 2. And by the great 8, I mean 8 electrons in their outermost shell, because that is what the noble gases have. The noble gases are helium, neon, argon, krypton, xenon, and radon. It's group 8A, so that very far right column of elements. So in order to form ions and be like the noble gases electron-wise, they need to gain or lose electrons. So for example, let's take a look at sodium. Sodium is in group 1A, and sodium is number 11, and it's in period 3. So if I sketch out a picture of sodium, there's the nucleus. First, it's got 2 electrons in its first shell. In its second shell, it's got 8 electrons. And since it's in group 1A, we know that it's got 1 electron in its outermost shell. But it would like to lose that 1 electron, because if it does, when this entire shell goes away, now this is the same electron configuration as neon, number 10. Now it doesn't become neon because it still has in its nucleus 11 protons because it's sodium. Neon would have 10 protons, but it's mimicking neon in that it lost that electron and now it has the great 8 in its outer shell. So each sodium would lose 1 electron, because this example said we've got 2 sodium atoms, which is going to be important for this compound that we're going to form. So how about sulfur? Sulfur is in group 6A. It's number 16, and it's in period 3. So sulfur has 2 electrons, 8 electrons, and its outermost shell has 6 electrons. Sulfur is really close to noble gas number 18, argon. It just needs to gain 2 electrons to have 8 in its outer shell. So sulfur would gain 2. So how does this all work in the atom world? Like, how do these guys actually form a compound? So I'm going to simplify my drawing of sodium and just draw the outermost shell. Actually, I'll just write Na in the center. So we've got 2 sodium atoms, and we've got 1 sulfur. Sulfur's got the 6 in its outermost shell, and it really wants to gain 2. So I'm going to draw 2 holes. So each sodium can give 1 electron to the sulfur. The resulting sodiums have a positive 1 charge, and now sulfur has a minus 2 charge. So if you take a look at the compound that forms, Na2S, you'll notice that +1, +1, and a minus 2 adds to make 0. And all ionic compounds have to have that stable 0 neutral charge. So now we can take a look at the activity in lesson 2.2.2. So I'm going to kind of skip over the start of this here to the meat, this table. And you'll notice here that going across for each of these compounds, they list the metal first, then the non-metal, and kind of what's going on with those. And then they list the compound that forms and the name. So let's check this out. Sodium, we just did a problem with that. It's got 1 valence electron that it would like to lose to form a positive 1 charge. Fluorine is in group 7A, and it's really close to being like neon. It just needs to gain 1 more electron. So fluorine has 7 valence electrons. Since it's in group 7A, it wants to gain 1, and then it will form an F-. So I call this the soulmate because Na's got a +1 charge. It wants to give 1 electron. And fluorine wants to gain 1 electron, so it forms a -1 charge. So when the two are together, we've got NaF, and they name it not sodium fluorine, but they change the ending to sodium fluoride. Let's look at a couple more here. Magnesium is in group 2A, so that means it's got 2 valence electrons. And since it's number 12, it's really close to being like neon, number 10. 12 minus 2 is 10, so it just needs to lose those 2 electrons, and it will form Mg with a positive 2+. Oxygen is in group 6A, so it would like to gain 2 because it's number 8, and if it gains 2, it will be like neon. And so if it gains 2 electrons, it forms a -2 charge. Another perfect match, MgO, because Mg wants to give up 2 electrons and oxygen wants to get 2 electrons. And the reason they stay together after is that positive and negative charge attract. And it's not magnesium oxygen, but the name is magnesium oxide. And by now you might be noticing that there's a pattern here in the oxidation states. That means the charges. Everything in group 1A forms a +1 charge. Everything in group 2A forms a +2 charge. Everything in group 3A +3. This is that plus or minus where it could go either way. Everything in group 5A wants to gain 3 electrons. Group 6A wants to gain 2. Group 7A wants to gain 1. And group 8A wants to stay as they are. So if you ever don't want to think, which I don't recommend, but you can always look at the pattern there and to write out your oxidation number. So let's go do some more. Beryllium is also in group 2A, so it wants to lose those 2 electrons and form a +2 charge. Fluorine has 7. It wants to gain 1 and form that F-. So now this is a little different here, and so is the one above it. Because fluorine only has a -1 charge, it wants to gain 1 electron, and beryllium wants to give up 2 electrons. 1 fluorine would not make that beryllium happy because there's still another electron it needs to get rid of. So that's why you need 2 fluorines, each accepting 1 electron, to make that beryllium happy and to form a neutral compound. Next one wants you to write out Mg and S. Magnesium has 2 valence electrons, so it wants to lose 2, so it can be like neon. Sulfur's got 6. It wants to gain 2 to be like argon, so it forms a -2 charge. Calcium also has 2 valence electrons it would like to lose. Chlorine is in group 7A, wants to gain 1 electron. Sodium's got 1 valence electron that it wants to lose. Bromine has 7, it would like to gain 1. So now we got to write our own compound. Sodium's got a +1, bromine's got a -1. That's the easiest. You just put the 2 together. So it will become sodium, not bromine, but bromide. Potassium's in group 1A, so it would like to lose 1. Since it's number 18 or 19, if it loses 1, it'll be like argon. Selenium is in group 6A, so it's got 6 valence electrons. It wants to gain 2, and it will form a -2 charge. So this one's tricky. Sodium wants to give up 1, but selenium wants to gain 2 electrons. So that means you need 2 potassiums, each giving up 1 electron to the selenide. Potassium selenide. A cheat way to do this is called the crisscross. Go over quick. So, for example, if you're trying to write out the compound for potassium selenide, if you start by writing the charges above each, ignore the charge and crisscross the numbers. So the 2 goes here, the 1 goes here, and you don't need to keep that 1 there, so it becomes K2SE. Let's do another one. If you've got aluminum and oxygen, you crisscross that 2 down, crisscross the 3 down, and you've got Al2O3 for your final compound. So that works every time if you need to crisscross, and you only need to crisscross if the charges don't cancel out. Aluminum's got 3 valence electrons that it would like to lose. Nitrogen has 5, so it would like to gain 3. And notice this is a perfect match. ALN. Aluminum wants to lose 3. Nitrogen wants to gain 3. So this makes aluminum nitride. Another aluminum. Notice that it follows the same pattern. Another oxygen. And I already showed how we crisscrossed to make Al2O3. But I also want to show you how the charges cancel out. So aluminum's got 3 electrons that it wants to get rid of. So if you just started off with an oxygen that wants to receive 2, you can see that this is not going to be a good pairing because there's still an electron that we need to get rid of. And if you make another oxygen, those always accept 2. So that's not working out either. So you need a second aluminum, and you need a third oxygen, to make everything work out. So you can see how it's Al2O3. And then as far as the charges go, since aluminum forms a positive 3 charge, and there's 2 of them, that makes a positive 6. And each oxygen forms a negative 2 charge. That makes a negative 6. Notice how these numbers equal 0 when you add them together, forming that neutral compound. Last one, we've got another aluminum, which is going to lose 3 electrons. And we've got fluorine, gaining 1. So you need 3 fluorines to make that aluminum happy, because each fluorine accepts 1 electron and aluminum has 3 electrons to give. This is aluminum fluoride. Can also use the crisscross method there. Write the charges above each, cross the 1 down, cross the 3 down, and then you don't have to write the 1. It's just AlF3. There's lots of patterns here, like the metals are always written first in an ionic compound. The nonmetals always go second. Also, the names always end in "ide." And charges always add to 0. Can you make a rule that helps you predict the composition of ionic compounds? One rule is if the charges add to 0, just write the 2 elements next to each other. You just slap them together. If the charges don't add to 0, crisscross. Let's do one more. Who are the perfect soulmates for strontium? Meaning they'll combine in a 1-to-1 ratio. So let's find strontium here. It's in group 2A. That means it wants to lose 2 valence electrons. Is there a group over here that wants to gain 2 valence electrons? Sure. All of group 6A would be perfect soulmates for that strontium because they all want to gain 2 electrons. Now you should be able to do that homework.